say, Europe has a massive problem right now, and the problem isn't limited just to this massive plebeian right here. The problem is also this. Between Russia's war with Ukraine, somebody sabotaging Nord Stream, economic sanctions to Russia, and Russia cucking Europe by cutting off energy and gas exports, 2021 seems like a holiday in the Caribbean with Emma Watson for a stepsister compared to 2022. And during this year of tripling energy prices, Germany decides to close its nuclear power plants, which is a move so stupid even the green girl herself dissed them for doing so. As a matter of fact, why don't we start building more nuclear power stations? Of course, it is somewhat problematic to start up since nuclear power stations are expensive, take up quite a lot of space, and present a lot of technological challenges. But in exchange we get clean, reliable, relatively low-cost energy for very, very long periods of time. Nuclear power plants operate for decades on end, and over their lifetime produce so much energy it's actually almost absurd. While stuff like coal has energy density of around 24 megajoules per kilogram of material, uranium-235 has 3.9 million megajoules per kilogram. A single standard 20-gram fuel pellet contains about as much energy as around 1,600 kilograms of coal, 1,120 liters of oil, or 960 cubic meters of natural gas. And as an additional bonus, uranium is pretty common on Earth, to the point of being considered a sustainable energy source. So why isn't nuclear energy hailed as the holy grail of energy production and used everywhere and by everyone? Well, one possible answer is that while nuclear energy is safest kind of energy, when it goes wrong, it goes really, really wrong. Places like Chernobyl and Fukushima are the most famous examples of this, with both areas experiencing nuclear catastrophes and as a result of that becoming hazardous areas for any kind of life for decades. But even considering all the nuclear power plant incidents, of which there have been over 100 since 1952, nuclear energy is still by a huge margin the safest kind of power, both to the environment and to life. Chernobyl in 1986, Fukushima in 2011, Kishtim in Soviet Union in 1957, First Chalk River incident in Canada in 1952, 3 Mile Island in USA in 1979, and Goiânia accident in Brazil in 1987 are the biggest nuclear accidents ever, and even combined with all other nuclear incidents. And considering all the damage that came from those incidents, nuclear power is still about 350 times safer than coal power, and is basically as safe as solar power. And combined with the fact it's thousands of times more efficient than solar, or any renewable energy source for that matter, it makes nuclear energy seem like a no-brainer when it comes to absolutely best kind of energy generation across the planet. Well, aside from safety, the biggest thorn in the side of nuclear energy might be the nuclear waste. The NIMBY, or not in my backyard mindset, is very prevalent in people who know the least about nuclear energy but shout the loudest, and it is a major reason to the gigantic pushback against nuclear energy. It's not helped by the fact that absolute majority of government solutions to nuclear waste problem up to this point were nothing less than idiotic and ineffective. During nuclear reaction, uranium is used up to produce heat and some byproducts. These products mostly consist of cesium-137 and strontium-90, along with some other elements like plutonium. And it's these products that are most dangerous and problematic to store long-term, since they remain radioactive for centuries. In addition to that, they also generate quite a lot of heat for decades. So, how do we store this waste? The main challenge to a long-term storage is placing it in safe area with no people nearby, safety from people gaining access to it for whatever reason, and future-proofing so it stays secure for centuries. That means the only real storage sites are deep burial sites, like deep abandoned mining shaft, purpose-built underground vaults, or, in this particular case, super-deep boreholes, like one of the deepest boreholes ever, Kola Super-Deep Borehole on Kola Peninsula, near Russian border with Norway, started in 1970. Over the next 25 years, Russians drilled to the depth of 12,262 meters, making it the deepest artificial point on the planet until 2008, when a deeper borehole was drilled on Arabian Peninsula. In 2008, the company that was responsible for the borehole was liquidated, and the borehole was completely abandoned. Now it serves mostly as a remote tourist attraction and barely anything else. The depth and, more importantly, the remote side of the borehole make this basically an ideal place for long long-term nuclear storage site. Theirs is already access road to the borehole site, and closest somewhat populated area is Zapoljarnij, a small town northeast of the borehole. The borehole itself is about 23 centimeters wide, 12,262 meters deep, and it gets hot at the bottom, at around 180 degrees Celsius. It might seem like a pretty high temperature, but it's not too much of an issue, especially when nuclear processes are involved. In nuclear reactors, nuclear fuel is used in form of nuclear fuel pellet. Average nuclear uranium fuel pellet is about 12 millimeters wide, 20 millimeters tall, and weighs about 20 grams. In reactors, nuclear pellets are used in form of nuclear rods, sometimes also called nuclear tubes. Every nuclear tube consists of nuclear fuel pellets, stacked on top of each other in a metallic alloy tube that is sealed from both ends. An average rod is about 14 millimeters wide, accounting for the width of fuel pellet and the alloy tube wall. Each fuel rod is roughly 4 meters long. And keeping in mind every rod is capped at both ends with some material, it means every rod is made out of about 190 nuclear fuel pellets, and with the weight of around 20 grams each pellet, every rod has a mass of around 3.8 kilograms of pure uranium, plus whatever is the weight of the tube wall itself. Let's assume it to be 8 kilograms, just to be generous. Keep in mind, rod and pellet dimensions differ depending on what reactor they are used for, but these are the average dimensions I've found on the internet. We know the diameter of the actual borehole is about 9 inches, or roughly 23 centimeters. It's not an exact value, and in some places the borehole may be narrower or wider, but that's an average. Let's just say the borehole is 22.6 centimeters wide, just to be safe and have a consistent number to work with. We also need to make sure the radioactive fuel rods don't directly touch the walls or they may be damaged, and we should also probably block some radiation from the rods from irradiating surrounding soil, but only to a point. Mostly we only need to block radiation close to the surface, as at deeper levels radiation will be naturally blocked by surrounding soil. So to make it simpler, let's add 2 centimeters of insulation material around the nuclear rods for radiation blocking. Since the borehole is 22.6 centimeters wide and 4 centimeters total are used for insulation, that leaves us with 18.6 centimeters of space to work with. We're gonna need some space later, so let's just say we've got 18 centimeters or 180 millimeters of space available for fuel rods, since we're assuming every rod is 14 millimeters wide. To account for width of both the fuel pellet and the tube wall, we can calculate that in 180 millimeters of space about 125 nuclear fuel rods can fit side by side. The space between rods can be filled with some kind of material, like concrete, resin, or some other material to basically glue the rods into one big unit. Also, let's add 5 centimeters of padding on top of each unit so that units wouldn't stack directly on top of each other and rods wouldn't touch, and keeping in mind the 2 centimeter padding along the circumference to block radiation from irradiating surrounding soil makes the final dimensions of a unit at 405 centimeters tall, 22 centimeters wide, each containing 125 fuel rods and weighing 1,475 kilograms. It is kind of heavy, but I have a strong feeling we've severely overestimated the weight of the nuclear tube itself, but that's what we'll work with. Besides, the insulation around the waste unit also weighs something, so 1,475 kilograms per waste unit is probably somewhat fair. The total depth of the borehole is 12,262 meters, but not all of that is going to be filled with nuclear waste. There needs to be some kind of padding at the bottom of the borehole so nuclear waste units would have something to stand on and wouldn't sink deeper into the soil, so we need something like a rebar reinforced concrete pillar. So let's subtract 10 meters from total depth of the borehole, giving us 12,252 meters of hole to work with. At this point a question arises, how do we lower something so heavy so deep without damaging it or the borehole itself? Obvious first choice is something like a crane, and since we need to lower something quite heavy quite deep, crane would have to be really big. Problem is not only the weight of the waste capsule itself, but the length of the cable required to reach such depths. Not just finding a suitable crane could be difficult, but producing a rope long enough to reach the bottom and support its own weight would also be extremely difficult, since even longest regularly used hoist cables are nowhere near strong enough and long enough to be used in such depths. But even if such crane and cable could be obtained, the problem is speed. Cranes are typically pretty slow when it comes to lifting stuff, especially lifting something as heavy as the cable required to reach the bottom of such borehole. We're talking about potentially thousands of tons in just cable. Some of the biggest cranes in the world can only lift super heavy weights at very low speeds, 1 to 2 meters per minute or so. At such speeds, just lifting the cable from the hole would take about 90 hours every single time, and that's not counting the time required to actually lower such weights into the borehole in the first place, including both both lowering the waste unit and lifting the cable back up, as well as actually fitting the unit onto the cable and various other necessary operations. It's quite possible depositing just one nuclear waste unit into the borehole could take several days per unit lowered. Of course, it would get faster and faster, as waste units stacking on top of each other would mean each consecutive unit would have to be lowered less and less, but still it would take months to deposit any considerable amount of waste and potentially years to fill capacity of just one such borehole, not to mention all the energy required to run such a massive operation. So, crane might not be the best answer we've got, but what else is there? Well, there's gravity. Obviously, we can't just simply drop nuclear waste into borehole and call it a day. But we can drop nuclear waste into a borehole in a controlled manner and call it a day. Since we calculated the width of the borehole to be 226 millimeters and our waste units are 220 millimeters wide, that leaves us 6 millimeters of space. That 6 millimeter gap is for air. The borehole isn't actually empty, it's full of air. And this is what happens when you drop something into a tube full of air. Basically, if air has nowhere to go, it gets compressed, and its density rises the more compressed it gets. In this case, air acts more like a liquid than a gas, and anything moving through liquid experiences certain resistance. The more dense air gets, the more resistance it puts up against anything moving through it. Even if such a heavy load as our waste unit was dropped into a tube of air, it will accelerate to high speed at first, but because of how small the gap is for the air to move out of the way of the waste unit, air below will get more and more compressed, gradually slowing down the movement of the waste unit. Of course, at certain level of compression, air will get too compressed for our waste unit to continue moving through it, at which point waste unit will probably bounce off. But then it will fall and compress the air again. High mass of the waste unit will increase the compression of air while also damping the bounce, which means it won't actually bounce as high as something lighter. And every time it bounces, waste unit will bounce lower and lower. Eventually, it will stop bouncing completely and just slowly move through now constantly compressed air at low rate of speed. That 6 millimeter gap between waste unit and wall of the borehole is where the air will flow around the unit, but because the gap is relatively small for the volume of air inside the tube, it means the waste unit will constantly encounter air resistance all the way until it reaches the bottom. And in the very bottom of the borehole, it's likely the waste unit will be moving very, very slowly, so the air has time to move out of its way, meaning the touchdown of waste unit onto the concrete pillar at the very bottom will be slow and relatively gentle, as a potential hazard to this method is that the more compressed air becomes, the hotter it gets. And while it probably won't get hot enough to actually have any effect on waste unit, there might be some damage to borehole walls, which would interfere with other waste units on their journey to the bottom. However, this is easily solvable problem since we can actually control both the descent speed and descent time of the waste unit by changing the width of the air gap between waste unit and the wall. If waste unit was falling slower, the air wouldn't get compressed as much and would have more time to flow out of the way of the unit, so the temperature would also rise at lower rates and to lower maximum level. If the gap was barely there at all, maybe like a millimeter or so, it potentially could take days to reach the bottom, but waste unit would move very gently and such descent would require no specialized equipment or external energy input. After a point, however, the volume of air in the borehole would become too low for it to compress enough to provide enough resistance to slow down waste units enough, but considering the total amount of air in the borehole, it would probably be relatively close to the surface, at which point waste units could be easily lowered using conventional cranes. We also must account for the insulation at the top of the borehole. Once it's filled in with waste units, we want to cap it off a decent distance from the actual surface, both to protect it from whoever might try to reach it and to block the radiation from going up the borehole. To block all possible radiation, we need several feet of concrete. For some reason, I couldn't find the exact number and metric, so I'm going to assume we need roughly 150 centimeters of concrete to block off all incoming radiation. And that is for regular, everyday, normal concrete. There are various designer concretes that are way better at radiation blocking, but data for those types is pretty hard to find, so let's just use regular concrete. Anyway, 150 centimeters of concrete is enough for radiation protection. But we also want to protect the nuclear fuel from being accessed by unauthorized personnel for whatever reason. We might also want to build something on top of the borehole site, since the top layer of boreholes is still usable land, so buildings or structures might be built on top of the boreholes. So let's just fill the top 100 meters of borehole with concrete. It will not only block the radiation, but could partially act as a support pillar for certain buildings. since it will effectively be a concrete pillar going 100 meters down into the soil in a very stable position. So after all that, the final depth of the borehole available for use is 12,152 meters, with the nuclear fuel units each measuring at 405 centimeters or 4.05 meters tall. We could fit pretty much exactly 3,000 units into the borehole. That means 375,000 nuclear fuel rods or 71,250,000 nuclear fuel pellets. The total weight of this entire mass would be 4,425,000 kilograms or 4,425 tons. Total nuclear waste mass would be 1,424.85 tons or 1,424,850 kilograms. The other 3,000 tons of material would be stuff like insulation and padding of waste units. It's actually very hard to find data on how much actual nuclear waste there is on the planet at the moment, but according to this article from World Nuclear Association, a total of 392,000 tons of high-level nuclear waste has been produced since first nuclear power plants began operation. We can round that up to 400,000 tons, out of which nearly 130,000 tons was reprocessed, meaning there's still 270,000 tons of the bad stuff left, which effectively means just the Kola Superdeep borehole alone can account for almost 0.52% of entire world's unprocessed high-level waste. Now, this might not seem like much, but there are several points we should consider. First of all, Kola borehole is not the only borehole out there. There are many boreholes in regions like USA and Asia, and even Russia itself has many more superdeep boreholes. Secondly, borehole storage is relatively cheap. Even drilling, transportation of material to and from borehole site, and filling the borehole with material is many times cheaper than building dedicated nuclear waste storage sites. It's hard to find exact data, but in 2016, U.S. Department of Energy funded $35 million to drill around 5-kilometer deep borehole in Rugby, North Dakota. Of course, it doesn't cost just to drill down, but there's also other expenses, such as wages, transportation of material, and people to and from the bore site. And in case of nuclear waste disposal, various expenses relating to that, like proper insulation of site, specialized equipment to handle radioactive material, etc. Let's just say it costs about $120 million in today's money to drill 5-kilometer deep borehole. Of course, the deeper you dig, the harder it is, so let's double that and add 25% for a super deep 12-kilometer deep borehole. In total, it would cost around $300 million to dig such a hole, and $300 million is basically pocket change, especially considering how much money has already been spent on ineffective solutions. For example, Yucca Mountain Nuclear Waste Repository within Yucca Mountain in Nevada has already cost around $13.5 billion over decades of construction, delays, and various issues, and not a single gram of nuclear waste has been stored within the facility yet. The total projected cost of the Yucca Mountain facility is about $100 billion. For that much money, we could drill about 330 super deep Kola-like boreholes. And just 194 such boreholes would be enough to store literally all the high-level nuclear waste ever produced up to this point in history. 330 boreholes would be enough to contain all high-level nuclear waste ever produced, and even an extremely large amount of medium and low-level nuclear waste. Or we could store all high-level waste up to this point and additionally store all high-level waste we'll produce in the next 50 years or so. Of course, drilling a borehole takes a long time and requires a lot of effort, but borehole drilling operations are somewhat small and relatively compact, especially compared to mega projects like Yucca Mountain. And Yucca Mountain is just one of the proposed nuclear waste storage facilities. Across the entire planet, there have been trillions of dollars spent on various projects, and so far very few ideas have turned into actual solutions. Besides, with how relatively compact and eco-friendly borehole projects are, it would be very possible to have multiple groups drilling boreholes in various locations at the same time across the globe. And considering that we can safely build structures on top of said boreholes, they don't even have to be in such remote sites as Kola. They could be located at sites close to the nuclear power plants or in areas reserved for future development. That would considerably decrease the transportation costs of people and equipment, and since these projects would probably take considerable time to implement, probably few years at least from planning stages to capping off the boreholes, they could create long-term work opportunities and boost the local economy. In general, it's considered that boreholes would be pretty much the fastest and basically the best way to set up nuclear waste disposal. As the third point, deep borehole disposal is actually least environmentally hazardous type of storage. According to Wikipedia, waste handling facility plus temporary security buffer zone only requires about 1 square kilometer of space, and after the nuclear waste is sealed, the facility can be dismantled and environment can be returned to pretty much pristine condition. Using boreholes as storage solution is even less environmentally impactful than just mining coal and other fossil fuels, let alone transportation, refining, and then burning non-renewable fuels in power plants. So yeah, we should start drilling more holes into the ground and burying our nuclear waste in them. But what do you think? Leave your comments down below and remember to subscribe.